Our next speaker is Frederich Hirzebruch, who is Professor Emeritus in the Department of Mathematics in the University of Bonn. He will speak on my joint work with Armand Borel from 1952 to 1954.
Where's some chalk? Yeah. Well, it's a pleasure to be in Princeton again, and I will report about my joint work with Armand Borel in the years 52 to 54. We were both members at the Institute for Advanced Study. Now, our joint work has a title, Characteristic Classes and Homogeneous Spaces, and was published in the American Journal of Mathematics in the years 58, 59, 60. But actually, all this goes back to the time at the Institute. I present a selection in the terminology of the 50s. So this more than 50 years ago, in the first third of the existence of the Institute. And, well, I use the old terminology and also the old methods, in particular writing on the blackboard. So I take a vector bundle E over the base space B, typical fiber Cn, and this vector bundle has a Chern class C of E, and it's a sum of the Chern classes in the individual dimensions. And the ith Chern class is an element in the 2ith cohomology of B with integral coefficients. Now we can always assume that we have here the structural group UN, the unitary group, and this unitary group then allows us also to have a Hermitian metric in all the fibers. And so now we can take the flag manifold, which is a unitary group divided by the maximal torus, and this maximal torus consists of all diagonal unitary matrices. And, of course, a point in this homogeneous space is an n-tuple of one-dimensional linear subspaces of Cn. And now it is possible to take the associated bundle with this flag manifold as fiber. So we can call this a flag bundle. So in this bundle, the typical fiber is this flag manifold. And the projection we call sigma. And now we lift our given bundle E to F. And now suddenly the bundle splits up into a direct sum of line bundles, so-called tautological line bundles, because over every point, if we take any fiber, this fiber is sitting over a flag, and this flag determines the splitting of the fiber into lines. And now we can take the Chern classes of all these line bundles. So we can call the first Chern class of the ith line bundle, we can call xi. And so this is in the second cohomology of the flag bundle. And then we can lift the total Chern class of E. And this is the same as the Chern class of the lifted bundle. And this then by the rules for Chern classes, which we assume known here, this becomes the product of the total Chern classes of our line bundles. And sigma star is injective. So whether to know C of E or whether to know sigma star C of E, this is equivalent. And suddenly the I's or the J's Chern class of the bundle E lifted becomes the J's elementary symmetric function. In the Xi. Now here we are very close to the thesis of Borel, which was published in Annals of Mathematics, 1952, to consider Chern classes as elementary symmetric functions. And yeah, this is also very important to determine the cohomology ring of Un over Tn. This is also part of the thesis of Borel. We can, you see, these cohomology classes Xi, they belong to the cohomology of F. The fibers of F are these flag manifolds, so we can restrict Xi to a flag manifold. Over a flag manifold, we have this Tn bundle, and therefore the n line bundles. So the Xi restricted to the flag manifold are cohomology classes of the flag manifold, and I will also call them Xi. And so then, therefore, I can take the ring over Z, polynomial ring in these X's, and now of the elementary symmetric functions in these X's, they come from the base B, and therefore they become 0 on the fiber, and so we can here divide by the symmetric functions in the X's of positive degree. So let's call this ring S plus. So in other words, all the symmetric functions of the Xi are being killed, and this is exactly the integral cohomology of the flag manifold. Yeah, so this is, of course, a very interesting algebraic object. You take the polynomial ring in n variables, and you divide out by the elementary symmetric functions in these variables of positive degree. Okay, so now in the spring of '53, I came to the office of Borel and told him some of my work. Namely, I wanted to study the tangent bundle of which I get as a bundle over F. Well, we cannot take the tangent bundle B as an arbitrary base space, but I have the fibers in F of F. And now this F has a complex structure, a natural complex structure, because instead of looking at n tuples of one-dimensional linear subspaces, I can take flags in the other way, that I take a one-dimensional complex linear subspace contained in a two-dimensional complex linear subspace contained in a three-dimensional one, and so on. And this obviously has then a complex structure. And then for each fiber, we can take the tangent bundle of this complex manifold. So this flag manifold bundle is fibered in such flag manifolds, and then we can take in every point the tangent space along the fiber, and then we get a vector bundle over F. And this vector bundle has, of course, as dimension the dimension of the Fleck manifold, which is n times n minus 1 over 2. The complex dimension of this Fleck manifold is n times n minus 1 over 2. And now the question arises, what is the total Chern class of the bundle along the fibers? So let's call this F with some triangle. I think we called it like this in the old days. The tangent bundle along the fibers. And this tangent bundle along the fibers also splits in line bundles. And we have to take this product. And so these are this many differences, xi minus xj. So I went to Borel's office and said that I needed for Riemann-Roch proofs such effect that the total Chern class of the bundle along the fibers is given in this form. And then Borel looked at this and said, well, here we have the roots of un. And while I had proved this not by the theory of roots, but by some induction, because this Fleck bundle can also be obtained as a tower of projective bundles, and I had studied this problem of bundle along the fibers for projective bundles. Okay, and now this led to some general theory for compact connected Lie groups G. We can take, if it has a rank L, we can take G, the maximal torus has then dimension L, and we can take this, we can also call it Fleck manifold. And now the points of TL, T is a product of L one-dimensional spheres, and a point on a one-dimensional sphere can be given by an integer modulo 1. And so we have actually over this Fleck manifold again L line bundles which correspond to x1 up to xl, to the coordinates we introduce on T to the L. And then the roots are certain linear combinations in these coordinates x1 to the L, which we can obtain by the adjoint representation. And so these are the roots. And then the result, which is actually almost the definition of the roots, is that the total Chern class of G of T to the L is actually the product of the roots. The roots become the first Chern classes of certain bundles, line bundles over G over T to the L. Now you see these coordinate functions I mentioned, x1 up to xl in T to the L, they determine the line bundles over the Fleck manifold, and the notation is very abbreviated here. These x's are used also as notation for the L line bundles I have, and then these are linear combinations in the x's like these. And then, well, I see I don't have very much time, and now there is the Weil group also operating here. In the case of the unitary group, the Weil group is simply all permutations, and there all the coordinates can be permuted, all the line bundles can be permuted. Also here we have the Weil group, and the Weil group is a group of linear transformations in the x's, and the Weil group permutes the roots, introducing certain signs. Anyhow, the roots are perhaps only defined up to sign if I don't specify the complex structure on G over T to the L. And the first Chern class, if I take any choice of signs for the gammas, then I have an almost complex structure on G over T, and I can take the sum of these gammas up to dimension m. M is the complex dimension of G over T. So 2m plus L is the dimension of G. And then the question is, when does this almost complex structure come from a complex structure? And what we observed, well, the specialists know this for other reasons, is that when I take this Chern class and raise it to the m's power and evaluate it on the fundamental cycle G over T, then I either get 0 or I get not 0. Yes. And in this case, the complex, almost complex structure is not integrable. And in the other case, it is integrable. It comes from a complex structure, and all these complex structures are related to each other by an operation of the Weil group. And now the question is, what is the value if yes, this, and put this very high up. This machine. So the question is, what is this other value? And in fact, in the integrable case, C1 over 2 to the m divided by m factorial is 1. Yeah, why is this so? Now, of course, Borel and I said we now know the Chern class of G over T, and by some other following method, one also knows the total Chern class of other homogeneous complex Hermitian spaces and so on. So one can apply to these are all projective algebraic manifolds. One can apply to these the Riemann-Roch theorem, which I was going to prove. The Riemann-Roch theorem was already formulated. One knew exactly how the precise formulas in terms of Chern classes and so on were, but it was not proved. But we still could apply it here. Why not? And there is also the special situation that here all Pontryagin classes of this differentiable manifold G over T vanish. Pontryagin classes only depend on the differentiable structure. And if the total Chern class is written as a product of linear terms, then the Pontryagin classes are the elementary symmetric functions in the squares of these roots. And the Weil group operates by permuting the roots and introducing certain signs. But for the elementary symmetric functions of the squares, it is obviously so that then these are invariant under the Weil group. And as in this example up there, that we have the polynomial ring in the axis modulo the elementary symmetric functions. To calculate the in the cohomology of G over T, we can throw away the invariance under the Weil group. But the roots are permuted, and therefore the elementary symmetric functions in the squares of the roots all can be put equal to 0. But these are by definition the Pontryagin classes. And so now, since the Riemann-Roch theorem, as we heard before, is so complicated, it is so that I better write it down only for the case that all Pontryagin classes vanish. And then it is the following. If we have, so projective, I proved everything only for projective algebraic manifolds. So suppose X is such a projective algebraic manifold with vanishing Pontryagin classes. And then let D be a divisor on X. And takes the holomorphic Euler number of X with respect to the divisor D. Well, I just say now that Riemann-Roch expresses this number in terms of all the characteristic classes. But this becomes very simple. Suppose D in H2 of X with integral coefficients is the cohomology class of the divisor. Cohomology class of the divisor. The divisor has topologically codimension 2 and determines the cohomology class. Then the holomorphic Euler number is simply D plus half the first Chern class divided by the dimension of X, suppose is M. So we take this to the m's power, divided by m factorial, evaluate this on X. That's the whole Riemann-Roch, as simple as this. If the Pontryagin classes are not vanishing, then you must multiply this with the roof expression in the Pontryagin classes. But this I can omit here, because this is simply equal to 1, the leading term. So now in the case of G over T, we can therefore take all the an arbitrary D in the two-dimensional cohomology of G over T and evaluate this expression. Now the first Chern class C1 of G over T is always divisible by 2. It's the sum of the roots. This reminds us already of Hermann Weyl. If we take it to the m's power, divide by m factorial, we always get an integer. So if we take an arbitrary two-dimensional cohomology class in G over T of dimension m, raise it to the m's power, divided by m factorial, we get an integer. So what are these integers? Now it is possible, these m's power evaluated on X, to write them in a different way. And then one sees that these numbers, cohomology class D in dimension 2 to the raised to the m power divided by m factorial, that these numbers are up to sign either 0 or they are the degrees of the irreducible representations of G. So suddenly Borel and I saw that these chi of xd, the holomorphic Euler numbers, have something to do with the representation theory of G. And while this had to be investigated much further, we also did some in this direction. I don't want to explain this here now, but there was a great development between the academic years 52, 53, 53, 54. Armand Borel saw André Weil in Chicago, and when he came back to the institute, he explained that one can actually, using the Riemann-Roch spaces for the divisors, get directly all representations of G, realize them in this way, and this became the Borel-Weil theorem. And also this was very much improved by Raoul Bott in the year 55-56, where Raoul Bott and Michael Attila and I were both all in Princeton. And so Raoul Bott did much work on this and improved all this very much. And yeah, then finally it was even possible to calculate the characters of these irreducible representations in connection with these general topological algebraic ideas. Namely, there was the Lefschetz theorem for the complex analytic case by Atiyah and Bott, and with this it was possible even to get the character formula of Hermann Weyl, which is very close to the Riemann-Roch theorem if I don't throw away here the A-Roof polynomials, because this expression with the A-Roof polynomials in it, so the Riemann-Roch written down as it is in full completeness, is essentially then Hermann Weyl's character formula. Well, these are the developments at the time, but Borel and I made many applications of these things, and I wanted to mention a few of them. Yeah, so I have to cut out several of them, but let me say at least the following. Yeah, take the 2n sphere, S to n. It has a tangent bundle, and tangent bundle of S to n. And the characteristic classes of the tangent bundle are, of course, well known, because everything practically vanishes. But now our methods, of course, included also the following, that if one has a bundle and applies to it certain representation of the structural group of the bundle, to calculate the characteristic classes of the associated bundle using this representation. This is essentially the same as looking at the character of this representation. And so now this tangent bundle T admits also the spinor group. Well, it originally admits the orthogonal group as structural group, but also we can use a twofold cover as a structural group. And to this we can apply the positive spinor representation. So then we get a vector bundle, delta plus of T. And so now we want to calculate the nth Chern class of this vector bundle. And it turns out that this nth Chern class is exactly n minus 1 factorial. Yes, n minus 1 factorial. So on the other hand, a bundle over the bundle over the two n spheres determines an element of the homotopy group pi to n minus 1 of the structural group. Now this has a very big dimension, this delta plus of T, so let's just write infinite unitary group. And now we knew that the nth Chern class of every vector bundle over the 2n sphere is divisible by n minus 1 factorial. Well, we knew it not quite. We only knew it up to a power of 2. So every vector bundle of the 2n sphere is a Chern class divisible by n minus 1 factorial up to powers of 2. And here we had now a vector bundle where the total Chern class is exactly n minus 1 factorial. So one could expect that perhaps this is the best one. It's always divisible by n minus 1 factorial, and this generates an infinite cyclic group in pi 2 n minus 1 of u. Well, one could also perhaps suspect, I don't think we did, that this is isomorphic to Z. Yeah. So now, later, in 1957, Bott periodicity was proved, and then it became clear that pi to n minus 1 of u is always equal to z, and that this element, which occurred in the work of Borel and me, is actually the generator. Also, in our work at the Institute, we could also write down certain exact sequences, and one example that came out is that pi 10 of u is 0 modulo a 2 group, modulo the class of 2 groups. And homotopy theorists had proved that pi 10 of u is equal to Z3. And then, if you look in Bott's collected papers, is the reminiscences there. He speaks of the spirited controversy between the topologists and the homotopy theorists. And Raoul Bott tells the story that in one night he was sitting there together with Arnold Shapiro to clear up this difficulty. And that there was also John Moore, and he bet $5 that the homotopy theorists were correct. And at the end of the night, this was in 56, 57, it turned out that Arnold Shapiro and Raoul Bott had proved that pi 10 of u is 0. Yeah, this is the story. But in fact, of course, the Bott periodicity says that this group is 0 for all even dimensions here, and is z for all odd dimensions here. So through these papers with Armand Borel, we came a little bit close to the Bott periodicity, and we came very close to the Borel-Weil-Bott theorem. All this improved by Bott. Now, other examples of, maybe I show one exercise we did, then I stop. Namely, a nice exercise is takes the homogeneous space U4, U2, cos U1, cos U1. Because we calculated also Pontryagin classes and characteristic classes for homogeneous spaces. And now you have this Grassmann manifold, U4 divided by, so U2 cross U1 cross U1. And this has two complex structures, complex Lie group divided by parabolic subgroup and so on in nowadays terminology. But we said, yes, there are two complex structures on it. One, you say the following: the space of all flecks of type zero-dimensional space, contained in two-dimensional space, contained in three-dimensional space, contained in the four-dimensional space, the only one we have. Yeah, jump 2, jump 1 in dimension. Now we do it the other way. Jump 1 in dimension, jump 2 in dimension, and at the end, now jump 1. So these determine two complex structures on this animal here. Now the question is, as exercise, calculate Chern numbers. This manifold has complex dimension 5. So there is, in the first case, the interesting Chern number C1 to the fifth, evaluated on the manifold in question. So let's call it X. What is this Chern number? Exercise, this Chern number is 4,500. Now you calculate this Chern number for the second case, other complex structure on the same manifold. People didn't know about the invariance of Chern numbers if one changes the complex structure. C15 on X for this complex structure is 4,860. That is, you see, this, of course, now you can make many more examples and take all these Grassmannians with their different complex structures and compare their Chern numbers with each other. Yeah, we also calculated the Pontryagin classes of, for example, the Cayley plane, which were not known. The highest Pontryagin number for the Cayley plane in dimension 16 is 39. And if you take the Pontryagin class in dimension 8, square it and evaluate it on the fundamental cycle, you get 36. So these are examples. And of course, there were many other things. We looked at all the possible definitions of Chern classes in the literature. There were exactly 7. We knew. And we compared them with each other because they were all usually with different signs. Up to sign, they're all fitted, but we identified them with the standard one we use all the time. Yeah, thank you.